Here we're going to revisit a problem we solved in a previous video. So it's question 5 from the 2018 Australian Mathematical Olympiad, which says if we define the sequence AN by A1 equals 1, and then AN equals N times the quantity A1 plus A2 all the way up to AN minus 1, our goal was to show that 2018 squared divided A sub 2018. And we did that pretty easily. It was a pretty short video, like 7 minutes. But what I really wanted to do was to really overwork it to find a closed form for this, and not find a closed form in an easy way, but find a closed form using something called an exponential generating function. And that's what we're going to do in this video. So I want to recall that we took this recursion and created this simple one-step recursion, which says n times a sub n plus 1 equals n plus 1 squared times an, but that only works for n bigger than or equal to 2. So in other words, that will not define a sub 2, but it's pretty easy to see from this recursion that a sub 2 equals 2. So that's good to know. Another thing that we're going to need, and this really kind of shows you how out there the solution is, we'll need the solution to a first order linear differential equation. So let's recall that if we had this differential equation y prime plus p of x, where that's any function, times y equals q of x, then the solution is given by y equals 1 over u times the quantity, the antiderivative of u of x times q of x plus a constant c, where u of x is the exponential of the antiderivative of p of x. In other words, it's e to the antiderivative of p of x. So this will be actually useful at the end of the solution. Okay, so let's get to it. So exponential generating functions are functions of this form. They're attached to sequences, and they're defined as follows. So for our sequence an, we'll have a sub n over n factorial x to the n. And notice I can start at n equals 1 because this is not defined for n equals 0. I guess we could define it as 0, but we'll just start it at 1. What makes it an exponential generating function is this n factorial in the denominator, and it's called an exponential generating function because if all of these are equal to 1, then we get something that's pretty much e to the x. Notice it is e to the x if we start at 0, it's e to the x minus 1 if we start at 1. Okay, great. Now, how do we know that an exponential generating function will work here? Well, that's because we've got this multiplication by terms that are like n or n plus 1, which are begging out to be canceled with things in the denominator. Okay, so we want to get this to the point where we can apply this recursion, but we can only apply the recursion for n bigger than or equal to 2. In other words, at a sub 2 plus 1 or a sub 3 or higher. So we're going to have to strip off the first two terms. So we can do that in the following way. We have x plus x squared, and you might think it should be x plus 2x squared, but notice that 2 is going to be divided by 2 factorial, so it's really just x squared. And now we have plus the sum n equals 3 to infinity of a sub n over n factorial x to the n. Now I want to re-index this thing a little bit so it looks like this left-hand side. So I can do that pretty easily. That's going to give me x plus x squared plus, now it's going to be the sum n equals 2 to infinity of a sub n plus 1 over n plus 1 squared x to the n plus 1. Okay, great. So now what we want to notice is that we are lacking an n in front of this a sub n plus 1, but it looks good other than that. So let's see, how can we get an n in front of this a sub n plus 1? Well, we could take a derivative, but that would give us an n plus 1 in front of this a sub n plus 1, but we want an n. So what if we just take this whole equation, a of x equals this, and multiply it by 1 over x? Then we'll have an x to the n term here. We can take that derivative, and that'll give us an n out front. So let's see. I'm going to write this as a over x. I'll leave off my dependence on x of a, but just remember that's a function. So that's going to be equal to 1 plus x. So that's how that simplifies. Plus the sum n equals 2 to infinity of a sub n plus 1 over n plus 1 factorial x to the n. Okay, fantastic. Now what we want to do is take the derivative of this. So let's notice that. So take derivative of both sides of this equation, and notice we have to use the product rule over here, so that's going to give us a prime over x minus a over x squared. So that's pretty easy to see. The derivative of 1 over x is minus 1 over x squared. That's going to be equal to 0 plus 1, so we've got 1 plus, and now we can do term by term differentiation on this series. So that's going to be the sum n equals 2 to infinity of n times a sub n plus 1 over n plus 1 factorial x to the n. Okay, and now we have this n times a sub n plus 1 term, and we have it for the appropriate places where we can apply this recursion. So I'm going to replace that n times a sub n plus 1 with n plus 1 squared times a sub n. Let's see what that gives us. So that's going to give us 1 plus the sum n equals 2 to infinity of n plus 1 quantity squared a sub n, and now this is over n plus 1 times n factorial multiplied by x to the n. Oh, and I just realized I took a derivative here, so these should all be x to the n minus 1. Good. Good catch. So now notice I factored this n plus 1 factorial into an n plus 1 times an n factorial. That's a standard thing to do here. Now the next thing I want to do is cancel a little bit. So notice I can cancel that n plus 1 down here if I cancel this down to a single exponent. And now we're left with this functional equation for a, which I'll go ahead and bring to the top, and we'll move on to the next step. So we achieved this formula. We've got a prime over x minus a over x squared equals 1 plus the sum n equals 2 to infinity of n plus 1 a sub n factorial, and then x to the n minus 1. Now the next thing that I want to do is I want to change this n so that it starts at 1, but that means I'm going to have to add and subtract something. So let's see. If I stick n equals 1 in here, I get x to the 0, so that's just the constant 1. I get 1 factorial, I get a sub 1, which is just 1, and then I get 1 plus 1, which is 2. So that means if I add 2 and subtract 2, then I can take this addition of 2 and move it into this sum, and then leave that subtraction of 2 out. So notice that's going to give me the following. I can do minus 2 plus 1, so that's going to be minus 1, and now I have plus the sum n equals 1 to infinity of n plus 1 over n factorial a sub n x to the n minus 1. But that's starting to look a lot like my original series A with the derivative having been taken. So let's see if we can manipulate that until we get that in the right form. So notice this is going to be minus 1 plus, now I can factor out a 1 over x. That's going to give me the sum n equals 1 to infinity of n plus 1 over n factorial a sub n x to the n. Great. But that looks almost exactly like my original series, but I have this n plus 1 here. But if I were to have taken my original series and multiplied it by x, and then taken the derivative, that's exactly what I would have gotten. So let's just write that out. Notice that is going to be the same thing as the derivative of the sum n equals 1 to infinity of a sub n over n factorial x to the n plus 1. So just to reiterate, x times a of x is going to be this sum right here. Great. And then obviously if you take the derivative of that, that n plus 1 is going to come down, and that's going to land you right there. So just to reiterate, this is going to be minus 1 plus 1 over x times the derivative of x times a, where I'll leave off my of x just like I did up here. But now I can use the product rule over here, so that's going to be minus 1 plus 1 over x times, so we're going to have x times a prime, and then plus a. Great. Like I said, using the product rule. Now we can distribute this through. That's going to give me minus 1 plus a prime plus 1 over x times a. Okay, fantastic. But now what I want to do, before we go on, I want to notice that that is equal to this. I can go ahead and cap these off and maybe multiply the whole thing by x squared to clear the denominator. And that's going to give me the following differential equation. So I'll have xa prime right here, and then minus a. So that's good for the left-hand side. And then on the right-hand side, I'm going to have minus x squared plus x squared times a prime, and then plus x times a. Okay, fantastic. But now I can move some things around. I really want to put it in this form over here. So notice that is going to give me x minus x squared times a prime. I get that from moving this x squared a prime over. And then I'm going to have minus x plus 1 times a, and that's from moving this x times a over, equals negative x squared. Okay, fantastic. Now the next thing that I want to do is divide the whole thing by x minus x squared. So that's going to give me an a prime here, plus x plus 1 over x squared minus x. Notice I use the minus sign to cancel this and flip this order. Then I have this is times a equals x squared over x squared minus x, which notice that is just x over x minus 1. Okay, fantastic. So I'm going to go ahead and bring that differential equation up, and then we're going to solve it using first order linear methods. Via a big calculation, we found a differential equation that is satisfied by our exponential generating function for this sequence an is given by a prime plus x plus 1 over x squared minus xa equals x over x minus 1. Great. So now let's get at solving this, and we're going to use these first order linear methods, which means we need to figure out this companion function first. In other words, this u, which is the exponential of the antiderivative of p of x. And let's just be really explicit here. P of x is being played by this, and q of x is being played by this guy. Okay, so we need to go ahead and find the antiderivative of p of x. That's going to be an important tool. And so that is going to be the antiderivative of x plus 1 over x times x minus 1. I'll go ahead and factor that like that. Okay, but we need to use partial fraction decomposition for this. So that means we're going to write x plus 1 over x times x minus 1 as a over x plus b over x minus 1. Let's go ahead and multiply by that denominator in order to clear the fractions. That gives us a times x minus 1 plus b times x. Okay, now notice that if you look at the constant terms on both sides of the equation, you get a equals negative 1, because notice the only constant term on the right hand side is negative a. That has to be equal to 1, so a equals negative 1. And then if you look at the coefficients of x, you'll see that b has to be equal to 2. And that's because a plus b needs to be 1. That means negative 1 plus b needs to be 1. That means b has to be 2. Great. So that means this guy right here is going to decompose into minus 1 over x plus 2 over x minus 1 dx. So that's going to give us twice the natural log of x minus 1 minus the natural log of x, which is equal to, using natural log rules, the natural log of x minus 1 squared over x. And you might say, where's our constant of integration? Well, we actually don't really need it here because it's built into this constant of integration in our final solution. Okay, so now we can exponentiate this. So notice this u of x is going to be the exponential of this antiderivative. In other words, it's going to be e to the natural log of x minus 1 squared over x. In other words, it's x minus 1 quantity squared over x. That's our u function. Great. So now that we've got this, let's go ahead and clean this up and then finish it off. Toward solving this first order linear differential equation, we found this companion function u was x minus 1 quantity squared over x. Now we're going to use this formula for solving a first order linear differential equation. So that means a of x is equal to 1 over u, so that's going to be x over x minus 1 squared times the quantity, the antiderivative of u, so that's x minus 1 squared over x times q, so that is x over x minus 1 dx, and then plus a constant. So let's see what we get when we do that. So notice these x's will cancel, and then this x minus 1 will cancel this down to just a first power. And then we can take the antiderivative of x minus 1 to give us 1/2 x minus 1 squared. So notice that's going to be x over x minus 1 quantity squared. And then inside of these big brackets, which I'll go ahead and put in that color, we'll have 1/2 x minus 1 squared. So that's that antiderivative plus this constant of integration, which is really built in the derivation of the solution for a first-order linear differential equation. Okay, fantastic. So notice if we multiply this through, the x minus 1 squareds are going to cancel. That's going to leave us with x over 2 plus some constant times x over x minus 1 squared. Now we are almost home free. We just need to figure out what this constant is. Notice that a of 0 is equal to 0. That's definitely an initial condition, but that's not super helpful in this case because that'll zero out the constant. Another thing to notice is that a sub 1 is equal to 1, but a sub 1 is the derivative of a of x evaluated at 0. And that's pretty easy to see from that formula up there. So maybe let's notice that real quick, that a prime evaluated at 0, that's definitely going to be a sub 1. That's true for any exponential generating function, but that is going to be 1. So we're going to use that as our initial condition. So I'm going to go ahead and take the derivative of this. So I'll do a prime of 0. We need that to be 1. Now let's go ahead and take the derivative over here. So that's going to give me 1/2 plus our constant c. And then that constant c is going to be multiplied by the derivative of this using the quotient rule. So that's going to give me x minus 1 squared minus 2x times x minus 1, and then that's all over x minus 1 to the 4th power, and now I need to evaluate that at x equals 0. So notice that evaluating this at x equals 0, well, this guy is going to zero out, and then this is going to give us 1 over 1. So we get 1/2 plus c. But now if we compare, 1 equals 1/2 plus c, which tells us that c equals 1/2. Okay, great. So let's clean that up, and then we will start the next board with this formula a of x equals this with c equals 1/2 plugged in. Okay, we're finally almost there. So we have a of x equals x over 2 times the quantity 1 plus 1 over x minus 1 squared. So I've simplified things up a little bit, but that's what we had from solving this first order linear differential equation with this initial condition given by the derivative of a evaluated at 0 equals 1. Okay, now what I want to do is re-expand this as a power series in order to gain a closed form for these a(n)s. So let's see if we can do that. So this is going to be x over 2, and then we're going to have 1 plus. Now this might look kind of harder to expand, but notice that that is just equal to the derivative of 1 over 1 minus x. Okay, along the way, we really use that x minus 1 squared is the same thing as 1 minus x squared, which allows you to see this derivative a little bit easier. Okay, now let's go ahead and expand this as a geometric series. So that's going to give us x over 2, and now we're going to have 1 plus the derivative with respect to x of the sum n equals 0 to infinity of x to the n. Okay, so but notice that's equal to x over 2, and then we're going to have 1 plus, and so now this is going to be the sum n equals 1 to infinity of n times x to the n minus 1. Okay, now let's go ahead and multiply this x over 2 through. So that's going to give us x over 2 plus the sum n equals 1 to infinity of n over 2 x to the n. But notice I've got an x to the first power in here as well. So I'm going to go ahead and strip that out. So that's going to be equal to the n equals 1 term is just x over 2. And now I have the sum n equals 2 to infinity of n over 2 x to the n. So all of those are going to combine together to give us x plus the sum n equals 2 to infinity of n over 2 x to the n. Okay, so now I'm going to go ahead and bring that up and we're going to make a conclusion. On the previous board we finally got this formula. A of x equals x plus the sum n equals 2 to infinity n over 2 x to the n. But recall that a of x was defined as the exponential generating function of this sequence. So it is given by, well, I pulled out this x term plus the sum n equals 2 to infinity of a sub n over n factorial x to the n. But what that allows us to notice is that not only do we know a equals 1, and that kind of stands apart from the rest of them, but we know that for n bigger than or equal to 2, we have a n over n factorial equals n over 2, just comparing these coefficients of x to the n for n bigger than or equal to 2. Great, but there is our closed formula for this sequence. We have a sub n equals n over 2 times n factorial. Great. So this was a ton of work, but we finally got there. And this is by no means the simplest way at getting at this, but I think maybe it's a nice way of getting at it because it allows us to explore so many different ideas that maybe did not seem related to this original problem. Okay, so that's a good place to stop.